Thank you very much, Sandra, for the invitation and for the very nice opening. So hi, everyone. So I must confess to you that I was expecting a very small audience with that we could discuss things more than me presenting things. So maybe I did the wrong set of slides, or I'm going to give the wrong talk. Nevertheless, I know that the community is, we are here in the middle of types, so it's a type community. So I have some slides about types, but my focus is more on the logical part of it. The type part of it, I leave to Delia Kessner and people that know what they're talking about. So I'm just going to show you more like what we've been doing. Ecumenical. So before I start with the ecumenical thing, I found this picture on the EuroProofNet page, and it was really nice because I was going to talk about in the women in the ProofNet session, and I saw that there are lots of women here, so I really liked this picture, so I decided to put it there. So it's nice to be among very nice people and collaborate with them. So the first thing that I'm going to do is to motivate a little bit this kind of work. So the first thing, and the questions are going to seem basic, and they are, but the answers, they are really far from being obvious. Okay. So the first one is, what's a proof, right? So when I teach logic to my students, I ask this to them, and they have lots of very interesting kind of answers. And then I put this example that I assume that you all know by heart, that of this theorem, that there exists two irrational numbers such that one to the other is rational. So we all know the answer to that. So this is provable. You have a proof. The proof is here. Okay, so I show this to them, and they're like, "Oh yeah, well, this is really nice." So you just take square root of 2 to the square root of 2. If this is rational, then you're done. If it's not rational, then you're done as well, because you take this one, and then you take the square root of 2, and then you have, at the end, you're going to have a rational number. It doesn't matter what, right? So, and my students, they come from computer science, now from philosophy, some from mathematics, a bit from mathematics, and actually they say, okay, this is cool. I mean, most of them never saw this before, and they're like, they really enjoy this kind of proofs, and this proof in particular, and they say, okay, this is cool. But if you ask for an intuitionistic mathematician, the person is not going to be really happy, because for an intuitionistic person, you have to tell if this is the case. I mean, if A, which is this number, is rational or irrational. You prove this first proof to me, and then this proof is okay, because we're not going to have this to decide this thing. We've already proved it. Okay. So there is a way around this, right? I mean, you could say, well, but this is a well-known theorem that square root of 2 to the square root of 2 is irrational. Actually, it's transcendental. You can take the 7 Hilbert problem, and then it's an instance of this, right? So then you can say, oh, okay, so nice. So let's go to the proof of this, the Hilbert 7th problem, and then I took this from the Even Needham book. It's 20 pages or more of proofs. And then you go, this is the theorem, and then you have many lemmas for proving this theorem. And then you go on, and you go on, and you go on. And then you get at the last page, at the last lemma, and you see that this is proven by contradiction. So then, whoops, an intuitionistic is not going to be happy about this anymore, right? So you see, I mean, even very easy questions may have very complicated answers. We're going to talk a little bit about this in the context of ecumenism, and I'm going to more or less try to show you where we can and how we can decide where we have to be constructive and where we can be classical. We have to be classical. Okay. So what's ecumenism? So ecumenism comes from the word Greek, which means the whole inhabitant. So it has nothing to do with religion. So it means that what we are looking for is a unique place, or a place where we can talk about different things, or things that normally they would fight between themselves. They can harmonically coexist. So this is the idea. every time I give this talk on different for different audiences on different perspectives, I get many questions of the sort, like what really are ecumenical systems, what they're good for, why should I care, and what's the real motivation behind the definition of this kind of systems. So I'm going to try to answer some of them today. And I'm going to start with Pravet's view of the thing, that he was more interested in the philosophical question of what makes a connected classical or intuitionistic logic. Okay, so this comes from inferentialism, and this was his motivation for doing the thing. And the thing about inferentialism is that, I'm pressing the wrong one. So that the meaning of the constants should be specified by the rules that we use, inference rules that you use in a proof system, for example. There are many ways there are many things that you could discuss there, like, for example, some things like harmony that I'm not going to talk about, separability that I'm not going to talk about, impurity that I'm going to talk a little bit. And these are things that people that work with inferentialism, they are often concerned. I'm not going to talk about all of these things because we're not going to have time. What I'm going to talk about is the difference between thinking, intuitionistic and classical thinking. So, for example, you can imagine a very nice dialogue between an intuitionistic logician and a classical logician. And the intuitionistic logician says something like, well, if by A or B you mean not A, not A and not B, then I can accept that A or not A is valid. So this is the intuitionistic person trying to figure out what the excluded middle is, right? But then the classical logician is going to answer, well, it's not really that, because I don't want to understand or to see A or not A as it's not the case that not A and not A, right? I don't want to put negation everywhere. So, for example, if I'm talking about Goldbach conjecture or any conjecture, it is even true or false. I'm not saying that it's contradictory to assert that it's not true, and that it's not true. It's not the case that it's not true, right? So you can see where this can go on, right? But then the intuitionistic logician says, okay, but at the end, for you, there's only one connective, right? One logical operator. So, for example, the Quine's dagger or Schaeffer's stroke. And then the classical logician is going to say, well, no, this is not true. They can be syntactically equivalent, let's say, in a proof system, but they are different in nature. So when I'm talking about A or not A, classically, I'm not really talking about it's not the case that not A and not B everywhere, okay? So they are not going to be the same thing. So this thing here is not really going to be the same thing as this thing here. We're going to see them as different, given by different connectives, or they're really going to be different in nature, okay? So this is the idea. So, okay, so in mathematics, we do this kind of exercise all the time. So we do separate when we can be classical and when we can be intuitionistic or constructive, and when we have to be classical. So, for example, we take this sentence here that if x plus y is to z, then either x or y is greater or equal to z in the real numbers, of course. Actually, you don't need. If you try to prove this in intuitionistic logic, if you see this intuitionistically, you're going to have problems because you don't know which one of these two you have to choose. So this is not going to make sense. For the classical mathematician on the other side, this is going to be okay because it's either one or the other one. And that dialogue, what it's saying is that okay, you can put a double negation in front of everything. And then this is the way that the mathematician is going to say, okay, so see, this is what I mean by the classical meaning of the sentence, right? So you can do that. If you do that, then you have a complete classical view of things. which is going to make the classical mathematician happy and the intuitionistic mathematician happy in the sense that the person is going to understand what it's written in there. It can understand, but it can do better because the first implication here doesn't have to be classical. This can be constructed. You show that you only need to be classical here when you're going to choose things, right? So then you can make both people really, really happy. So this is the idea of using ecumenical systems in mathematics. Actually, Krauss did a very nice work on this, on axioms of choice and other stuff, more complicated mathematics that I'm not going to talk. I don't have time to talk about this today. And then you can play this game of seeing when you have to be classical, when you have to be, when it can be intuitionistic. Okay, so the thing is that, so there are many mathematicians, I'm sorry if this gets a little bit philosophical, but actually it's not. I mean, it is and it's not. So what I'm quoting here is not, it doesn't come from philosophers, but from well-known mathematicians. So it's true that mathematicians often prefer direct proof over proof by contradiction. And the reason is that when you prove something directly, you assume something, and then what you do is you make steps of proofs from one to the other, and in each step you're going to reduce things from one step to the other until you get here. And in each step, you know what you're doing. You understand what you're doing. Right? When you do the contrapositive, what you do is a mix. So you have here a direct proof, but of a negation of something implying the negation of something. So what you do is that you still have some steps here, but this proof is going to tell you what else must be true in words where Q fails, right? So it's not completely direct, but still has some direct steps in there. But it's going to miss something because you're going to assume and prove negations. When you prove something by contradiction, on the other hand, you don't have any information. You may still have some argumentation in the middle, but the thing is that you assume two things, and at the end you enter an empty state or punctuation mark, or you may meet a wall or something like this, and then you're done, right? So this is not really satisfactory, truly, I would say. And this is not only my view. This I took from David Hampton's in Math Overflow. And a similar way of thinking is given by, and I'm going to pass this quickly, by Pimentel, also in Math Overflow, where he's talking about the differences between the approaches is that the direct, you go from one to the other, as I said, you go forward. The contrapositive, you start backwards, and then you reach A. And in contradiction, you go in the middle is a kind of strategy. So you go from one and the other, and you're somewhere in the intersection of these two things. Okay, so in this talk, what I'm going to do is to show you what means to be classical and intuitionistic in logic. So I'm going to talk about logical connectives. I'm going to scratch only ecumenical types, and this, as I said, this is still ongoing with work with Dalia Kessler, Mariana, and me. And then if I have time, I think I will, because I was planning to go slower, but not with you. So I don't have to pass through many things in the middle. I'll talk about modalities, which is a work with Sonia Mahan, with Carlos Pereira, and Emerson Solis. And surprisingly, it's not published yet. It should be published later this year somewhere. We have some things already done there, but not the final result. Don't look at this. I mean, it's a lot of stuff, but some of them we're just going to jump, so don't worry. So let's, like, now I talked about philosophy, I talked about mathematics. Let's now talk about logic, right? I came here to talk about logic. So for a classical logician, we have this Middle, of course. And what does it mean that this holds in classical logic and not in intuitionistic logic? Well, you could say that, so if you take sequence systems for classical and intuitionistic logic, so for example, in intuitionistic logic, the one that restricts the succeedant of a sequence to have only one formula, you see that here you can prove only because you have the possibility of changing the disjunction by a comma, and then you're done with the proof, seeing the proof bottom up as theorists should. But if you try to do the same here, you're doomed because you cannot have more than one here, so you cannot put commas, so you have to choose, and whatever you choose, you're doomed, okay? So this is the idea. If you look at this, you already see, okay, it's different, right? And Gensen would say, okay, the problem is the disjunction. So, the disjunction is different. My harder, for example, if you take, instead of taking this single conclusion sequence system here, you may have the comma, but then when you have the implication, you restrict the number of things that you have here. And then you would say, okay, no, the problem is implication. Kravitz actually says that the problem is. So it's not really a problem. I wouldn't say problem today. I would say the difference is disjunction implication, and in Kravitz's opinion, it's both. Actually, what he affirms is that both logicians, they are not talking about the same things. Okay? And I love this quote by Kravitz. He says that the classical logician is not asserting what the intuitionistic logician denies. The classical logician asserts that A or not A is valid classically, to which the intuitionistic does not object because he sees this as double negation anyhow. He objects to the universal validity of A or not A intuitionistically or constructively, which it's not asserted at the first time by the classical logician. So they are not talking. But this is the idea. So what Kravitz did with this was to propose natural reduction, where the two things could coexist in peace. The thing is that as I said, some connectives are not going to be the same for him, like into disjunction or implication in the first order extension as well. But others are going to be the same, so they're going to be shared. So the conjunction and the universal quantifier and negation, they are going to be shared. So these are the shared connectives for Kravitz, and they are going to be shared between classical and intuitionistic people. And the intuitionistic they are going to have their own connectives for implication, disjunction, and existential. And the classical are going to have their version of the same connectives. And the rules in natural reduction are this. Okay. Well, these rules here are just the rules that are used with the natural reduction system, Gensen, and then that Kravitz studied in his PhD. These are kind of odd because you're going to define things using negation, you put negation everywhere. And you could say, okay, this is only double negation translation. We're going to talk about this later. Okay. Well, so if you have the system, you can prove things like, for example, why there's only one negation, because you can prove that implication to bottom classically and intuitionistically are the same. You can also define, as we put in the beginning of the talk, you can define actually the classical connectives using the intuitionistic ones. But there are many things that you cannot do. So for example, you can prove that intuitionistic implication implies classical implication, but not the other way around, so they do not collapse. And this is a real challenge when you mix intuitionistic and classical logic, how you don't collapse them into classical normally, okay? So it doesn't collapse. And you have other stuff. So for example, you have that not A implies A if this implication is classical, but not in general if it is intuitionistic, and etc. You have what Luis Carlos calls this the modus ponens. I don't. That if you have A and A implies B intuitionistically, then you have B intuitionistically, which is okay. But you don't have that A and A implies B classically. You have B intuitionistically. You shouldn't have anyhow. So I don't call this modus ponens. Luis Carlos does anyhow. So you can see that there's difference. You can now differentiate what's intuitionistic, what's classical using this proof system. And actually, you can prove things like, for example, that this thing is provable. You can only if the conjunction of the things that are on the left implies intuitionistically the thing that is on the right, that is entailment is deterministic. But the entailment becomes classical if this A is what we call classical at some point. So you have both. You have both behaviors, classical and intuitionistic, depending on what you're dealing with, what you're trying to prevent. Okay. Yes.
How do you handle that relationship? You don't see on the negative statements and
Double negations, right?
the fact that that is from both that's the level.
Yes.
Well, it's purely negative statements in your opinion. So I'm not sure how you could be able to prevent or I don't know if you can really prevent a relationship.
Double negative by then, no.
Like not follow, not by normal follow. Yeah, the thing
yeah, just a second. I don't know where I have anything over. Okay. So what do this is provable. If this is classical, then this is always provable.
But that only makes the mutation between the mutation and the 425. Yeah, and it's something that's really pretty on the text level because to do that.
Yes.
Yeah.
That's what she's saying too. If you put the C here, then yes. Not into statistically. Yeah, I think I understand. I really don't have a word here, otherwise I would do the math. But yeah, so one thing is that if you have everything classical, you have the classical implication, classical existential, and classical disjunction, and all the other ones, the neutral ones, then in private system, you collapse to classical logic. So I have first order classical logic. It's a conservative extension of classical logic. Yeah, in his system. Yeah. You're good. Okay, so first law. So we all know that this is provable in classical logic. This is a proof in Coq of the thing. And this is the proof without Coq. Well, sorry. This is the proof of Coq in classical logic, and you can do the same in ecumenical logic. The only thing is that you have to be careful a little bit about the implications. So if this one is classical, then you can prove the first law as well. And this is the proof in private system, where it's the same proof that you would do, for example, in classical logic, more or less. But you don't have the double negation rule here, so it's a little bit different. But well, you can do it if this thing here is classical. The thing is that, as in the proof of, for example, Jensen or David's system for natural deduction for classical logic, for proving this, you need to have the negation. You have to discharge, introducing and discharge a negation here. Okay. So you have a rule, a formula which has only implication, and you use negation to prove it, which is not good, right? So what we did was we changed a little bit the perspective towards private system, and came out with a complete pure system, which we don't use negation for defining kinetics. Okay, classical kinetics. So there are two ways at least to do that, to purify this. There are more than this. There are 3 or 4 that I know of purifying this. So instead of defining the existential quantifier using negation and the universal quantifier, we can use polarities, which I'm not going to talk about today. Or, and this is the thing that we're waiting still to be published. Or we can use something that is called Stoop, that comes from the word from Jihan, also from the word of Martian Marigot, which would be in a sequence. You're going to have now multi-sets of rules, or sets of rules, it depends, where they're going to be separated by a semicolon here. And here you're going to have lots of formulas. It can be a set or a multi-set. And here you may have 0 or 1 formulas, or at most 1 formula. Okay, so it's not a sequence, it's just a formula with let's say annotated. You have some other formulations of that. So for example, you have the out rules and things, other ways of talking about this. I'm going just to talk about this too. And the idea is the following, that if I want to prove this, and I do things bottom up, as I said, as a proof theorist, if I want to prove this, what I'm going to do is I'm going to add to this context here, which I call a classical context, this formula, and I'll do as I would do, choose choose a term to continue on with my proof, okay? I forgot the name, sorry about that. Huh? Weakness. Yeah. Okay, so this would be, you can say, okay, but this is the same as, for example, sequence systems for classical logic, yes and no. All systems of Berg, Restall, and some other systems by Gavai as well, they have the same kind of idea behind, but they're all different somehow. So this is the one that Girard, mostly that Michel Paquibot uses in this lambda mu calculus. It's exactly the same idea. If you are in types and you're aware of lambda mu. Okay, so I'm going to finish soon. So there's some other things that I'm not going to talk about, that it's going to towards his observation that for products you have this equivalence that is really unfortunate and allow you to do things that we wouldn't unlike it to do and things like this. But I'm not going to talk about this today. Okay, so so the idea is just that. So instead of having one formula, you're going to have a multi-set or set of formulas and a distinguished one that we're going to call this two. And then you have a set of rules that they don't use negation anymore, or they don't define any connective in terms of any other connective. Okay, it's completely pure. And then you can do many things with this. So for example, you can prove strong normalization and things like this. And you can also prove that this is actually what you're doing is just to pass this to the other side negated, although it's not really what you do. I mean, there is a correspondence, but it's not operationally is not the same thing. And so I'm not going to enter into details because I'm going to finish with the type system. And then you can revisit, for example, first, you can prove things like the first rule, now you see that you don't use negation. It happens the same with Greg's system or Gavai's system as well. And the difference between their system and our system is that here we can have everything classical, for example, but we can have here classical and here I don't care. Here can be anything. So the idea is, look, no negation. Yeah. Okay. So what we can do with that normalization, as I said, a very Howard correspondent, I'm going to really quickly to present it. And we can do things, and we can show that what we have at the end is not double negation translation. Then we're going to lose some properties and things like this, but I'm not going to discuss this. And I'm not going through modalities. So I'm going to finish this talk on ecumenical terms. So this is just the beginning of the work. It has been a while, but the thing is that we all have many things to do and other objectives in life. So we come and go with this. Hopefully we're going to finish this year. So the terms that we're going to have is we're going to mix classical and intuitionistic terms. The idea is to have both operators, right? Constructors. We're going to have lambda and we're going to have a mu. So we're going to have names and we're going to have terms and variables and things like this. And we're going to have a distinguished operator that we call activation operator, which is this one. Okay, I'm going to tell you more or less what happens. So so these are the terms. So we have lambda, we have mu, we have substitution that they come into two flavors, depending if the thing that you have here is really a term or a command, right? And you have the two constructors, as I said, and you have this activation operator here that's going to handle wiki, because we need wiki. So the system is this one. So the term system that we have is this one. So we have judgments, and then this is Delia's fault because she prefers to put the stool closer to the consequence symbol. I don't know why. I mean, I'm sure the other way around, but I know people in both communities that do that. So I don't know which one I prefer, to be honest with you. So just to tell you that this is a stool now, and this is the set of formulas that we have, and these are the set of rules that we have. So you see, I mean, more or less we have what we would expect it to be. Here is just the lambda abstraction. Here's the move. So see here you have a comment here. And the thing is that this C here is really going to deal with the bottom because we need to deal with the bottom. And you can see here that connected that activation operator there is going to handle the weakening here. So every time you see this, it means that you can forget about the formula that you have in the stool. Okay. And then we're just going to do this for implication. So you have implication intuitionistic and classical. And this is the general version of the elimination rule for the classical inclusion. Okay, so this is, as I said, just the beginning of our work. So I don't have much to say about it, other than we have examples. So for example, Chana, we have burst again. So if everything is classical and you have that piece of proof there, then you can prove that this first term here has this type here. You can do the same if everything is intuitionistic. Oh, this is not fierce. I'm sorry. This is not fierce. Sorry. I was going to put fierce and I didn't. I forgot about this. So this is not fierce. This is just this is just weakening. So this is just a weakening with everything classical. And we have weakening with everything intuitionistic. I'm sorry about this. I have the other one. And this is first, but this is not. Oh, sorry about this. Sorry about the confusion. Yeah, we are going to show first. So this is first, everything classical, and the context is this. So it's not the same thing that we have here. It's just this part here. Now it makes sense. So this part here is just this, and this is first classical, and this is the proof using terms. And now we're going to have the first that is going to mix things intuitionistic and classical. And this is the context that I'm going to have here, which is this part here. And this is the proof of the first law, having only the last one classical. Okay, I'm not going to have time for modalities. I'm sorry about this. This is work. This is the work that I've done with Sonia Marin and Luis Carlos and Emerson Sales. And the thing is, how do you mix modalities as well, other than propositional or first order logic? But well, this is for another time. How much time do I have? Oh, I thought I was going until 3. Oh. Okay, but anyhow, I mean, sorry about this. Anyhow, I'm going to just show you in a nutshell what this is. I'm not going to tell you what model logic is because you know what model logic is, and so I have a set of slides for kids. And the thing is that, so as I said, ecumenical systems, the whole problem is how do you mix things and you don't collapse? How do you mix modalities, classical and intuitionistic, and they don't collapse? So the thing is that when you have classical logic, and talking about proof theory, but also talking about predict semantics, right? So when you have classical model logic, right, what you have is that you have propositional classical logic plus this axiom here. Modus ponens and necessitation. And your semantics is really easy. I mean, it's a quick semantics based on relational structures, normal stuff that we all know about this. And you have all the dualities that you could have. So, for example, we have that you can find box in terms of diamond, vice versa, and things like this. Okay. Now, when you go to intuitionistic model logic, then you don't have this duality anymore. They are completely independent. And what are you going to put on the top of intuitionistic propositional logic. Of course, you put the K as you put before, modus ponens necessitation, but you need some other stuff, right? So if you only do that, and then you're going to need now what we call bi-relational structures. There are some other ways of doing this as well. Not going to discuss this. You need this kind of closure in the sense that saying that if you go this way and then this way, then it should be a word here that you can go and then right. And this is for guaranteeing things like, for example, monotonicity of the diamond and things like this. But of course, I mean, this is only about the box. As box and diamond are independent, you may have other axioms that you put here that are going to change completely the kind of logic you're talking about, right? So, for example, you may have this two, the K that we had before plus this one that's going to deal with modalities that Newland has CK of each. And still you have the same semantic configuration. But you can put some more axioms. So, for example, you can add the distributivity of the diamond with respect to this junction, and then this is the zero area of this thing. And then you're going to need another closure condition here, which tells you it's a confluence kind of thing that's saying that diamond kind of thing, saying that if you go up and right, then it should be a word there that you can just close the diamond here. Okay, but you can still put something else that we can call, which is this axiom that is it's a kind of K to the reverse with a diamond, etc. And then this is also enough for talking about the set of modalities, and this is what is nowadays called intuitionistic modal logic. And you have the notion of what is the box using this, right? And diamond and etc. Okay, and it's missing something. Okay. Okay. When you go to proof theory on the outside, in classical modal logic, what you do is just to add this rule here. If you go to intuitionistic modal logic, if you only have K, then this is also enough. But if you add axioms, then you need to add other rules as well. So if you only add this one, then this rule is enough. If you add the disjunction, the distributivity of the disjunction, then these rules are enough, according to Sonia. And if you put K4, then there's no way to do that. Okay? So you don't have a problem on the model type theory, the model theory side, but you have a problem on the proof theory side. And the way of doing this is just to put labels and then you're done. There are some other ways of doing this. I'm not going to talk about this today. But you know, the well-known is system, the Simpson system, where you just put labels and you're okay with this 5 axioms here. Okay, so how about the ecumenical model? So to finish the talk, just to give you an idea, the idea, and I must confess that I've been moving away from this, but I don't have strong results right now to present to you, so I'm not going to even try. So this idea that we had back in 2021, I think, was, okay, just put everything in first order logic, right? So if you can see box and diamond in first order logic. And the thing that Simpson said is that depending on the logic that you put here, then you're going to characterize a modal logic on the other side. Okay, so if I put here classical first order logic, then I have classical modal logic here. If I put here intuitionistic modal logic, then I'm going to have intuitionistic modal logic here. And then the idea that we had was that if I put ecumenical logic here, first order, then I'm going to have ecumenical modal logic for this. Okay, so this was the idea. It's a straightforward one. So just did the same thing as Simpson did. And then we have, as we're going to have 1 pro and 2 existential quantifiers as outermost quantifiers, we're going to have 1 box and 2 diamonds. You could say, oh, how about this implication and etc. Well, I'm not going to discuss this. There are other options, but this one is reasonable. And when we do that, you see that they're independent. So if everything is classical, then you have the double negation thing, determinability. But if you are intersynesthetic, then you don't have it anymore. In particular, they're not you cannot define the intersynesthetic and classical diamond one from each other. Okay, so then we can go ahead and give ecumenical biovariation structures, and I'm not going to talk about this. We can give label modal rules for these things. We can use negations, a la rabbits. We can do extensions with this stuff, rules for this stuff. And there's some fine lines that we have to be careful not to cross, but I'm not going to discuss this because you can, again, collapse classical, intersynesthetic into classical, ecumenical into classical really easily if you do stupid things. I'm going to finish this just telling that in the same way that we did we purified private system, we can purify labeled mode of systems. So instead of having negation here and box, I can have this two, which now it's on the other side, and the classical systems are going to work like this, same way as before. So now I'm ready to conclude. So the future. So I talked about briefly about many things. Just the surface of things. There's many other stuff that I didn't even mention. So the first thing that we've been thinking now is coming back to the first slides, that'll be to do real ecumenical mathematics. So we know that if all operators have a constructed reading, the axiom choice is a theorem in Martin-Wolf type theory. What would happen if we have hybrid readings of single functions? Things like this. I put there axiom choice, but you can do whatever. So for example, you could think about arithmetic and things like this, right? These are things that we don't have an answer. So this would be interesting investigating. This was really the motivation of someone called Krauss. Applications in computer science. So there are many. The whole group, so Europrofets, great part of what people there do is exactly to have ecumenical systems, so they can use the ducti to talk with different kind of, they have ecumenical perspective, so they can use the ducti to talk with other proof of systems. So for example, Koch or Isabel, et cetera, et cetera, et cetera. So there's the PhD thesis of MEV that was really focused exactly on this. It's not the same system. It's not for human people to read. It's for computers only, eyes. But then this has been used in computer science like quite a lot. Not me, because I'm not capable of. You saw proof in Koch that I did that proof, but this is as far as I can get. Okay, but there are serious people doing serious things using ecumenical stuff, which is really nice. So I don't plan to go there, but there are people already doing that. There are some other questions of when you talk about ecumenical stuff, I only talked about classical and intersynesthetic, and how about other stuff? So there are some other people doing some other stuff. So for example, the postdoc that we have in our group now has an ecumenical system for intersynesthetic and minimal logic. Cristina Sagrada and John Rasga have an ecumenical system for intersynesthetic logic and SPOL. And there's actually work in the direction how to systematically connect translations to ecumenical systems. So every time you have a translation from one logic to the other, you can have a system that combines them, for example, which is interesting. And semantics, finally. I mean, there are lots of things going on there. So we just submitted a paper with Victor and Luis Carlos on proof-theoretic semantics. Not going to talk about this, so don't worry. Which really gives really the meaning of philosophical meaning, really, or not only of the difference between classical and intersynesthetic connectives, but also classical and intersynesthetic groups. And we do that using semantics, which is neat and nice, I think. But I'm not even going to try to talk to you about this. And with Marcelo Canino, and Luis Carlos, we have a heightened kind of ecumenical heightened semantics, for first order logic, ecumenical logic. So there are some other stuff that I could put there, but I think that this is enough. So I'm going to stop here. Thank you so much.